So let's now move on to part 2 of our proof of linearity. So again, we're going to have a function f that is going to be Riemann integrable over the interval ab, and we're now going to consider the function minus f, which is going to be defined in the intuitive way, so it's going to carry any x in the interval ab onto minus what the function f will carry x onto. So minus f of x is just equal to minus f of x, which is perfectly intuitive. So what we now want to prove is that this function minus f is going to be Riemann integrable over our interval ab, and that the value of its integral is just going to be minus the value of the integral of f over the interval ab. So to do this, we're going to need another result about suprema and infima, which we alluded to when we were looking at the supremum infimum result previously for part 1. So we'll have our set x again, and let's now consider the set minus x, where this notation, and instead of using y, I'm just going to actually use this notation for our second set instead. So this notation is just going to denote the set where you take all the elements in x and you multiply them by minus 1. So it's minus little x, where little x is an element of capital X. And the results that we're going to need are what is the supremum of this set minus x and what is the infimum of this set minus x. And the answer is that this is equal to minus the infimum of the set x, and this one is equal to minus the supremum of the set x. So you can compare and contrast that to the previous result that we had. So the minus is perfectly expected. That's exactly as you would have predicted from the previous result, where you just had lambda here, because lambda is now minus 1. But because it's now negative, we are doing this different thing now, where we have to, instead of putting supremum here, we have to switch to it being the infimum. And drawing a picture with an example illustrates perfectly why this is the case. So again, let's just take the set that we had previously, so the interval 1, 2. So here's 0, here is the interval 1, 2. Then if we take minus x, that's going to be this set, so minus 2 to minus 1. So minus x is the interval from minus 2 to minus 1. And you can see how the supremum of this set corresponds to the infimum of this set, and the infimum of this set corresponds to the supremum of this set. So let's just check this. The supremum of negative x in this case is minus 1, which is equal to minus times the infimum of the original one, because the original one's infimum is 1. So that is beautifully working there. And let's check this one here. So the infimum of negative x is minus 2 clearly, which is equal to minus times the supremum of x, which is 2. So minus times 2 is minus 2. So it's working beautifully in this example here. And you could generalize this, by the way. If you took a general lambda is less than 0, then you could stick in here lambda instead. In this case, lambda is just equal to minus 1, which is why there's just a minus 1 there. But for a general lambda that is less than 0, you could put in a lambda there. However, it's not really necessary to do that, because just like how in our linearity proof we divided it into these two separate bits where we had lambda greater than or equal to 0, and then we're just proving one result for where lambda is less than 0, which is the negative 1 result. And then those two together mean that we have it for all lambda multiples of f, because if lambda is less than 0, you can just split it into the minus 1 part and then the modulus of lambda, which is a positive part, and then you can just apply the two separate results one after each other to get the overall result. And similarly here, if we just have this result, we can then have the result for a general lambda of x. So if you consider the supremum of lambda of x for a general lambda where lambda could be greater than or equal to 0, or it could be less than 0. If it's greater than or equal to 0, then you just use the result that we had in the previous part. If it's less than 0, then you can just split it up into the supremum of modulus of lambda. Oops, let me rub that out. In fact, I'll rub it more out. So supremum of the modulus of lambda times minus x. And then you can firstly find out what the supremum of minus x is using this result. And then if you want to know what the supremum of the modulus of lambda times minus x is, you just then apply the result that we had from the previous part, because lambda is now greater than or equal to 0, but now your new x that you're applying it to isn't the original set x, it's minus of x. So you can just split it up into these two separate parts. So actually, all we need to do is prove this single result, and then we'll have the necessary tools to be able to work it out for whatever lambda you have for all lambda less than 0, because you can just split them into this minus part and then the modulus of lambda afterwards. You can use the two separate results to get it for any lambda. I hope that makes sense. So what we now want to do then is prove these results, and again the proofs are going to be very similar, so we'll just go through one in detail. We'll do this top one and then I'll just talk through the second one. So let's prove then that the supremum of negative x is equal to minus the infimum of the set x. So we need to prove then that this number is 1, an upper bound for the set minus x, and 2, that it's the least upper bound. So let's start with it being an upper bound. So let's do again by proof by contradiction. So if it's not an upper bound, then that would mean that there is an element in the set minus x that is strictly greater than it. Now everything in that set minus x is of the form minus little x. So that would mean that there is a minus little x that is strictly greater than minus the infimum of the set capital X. If it were not true that this is an upper bound for that set. On the picture, here we are here. So in yellow, I've added there, this is this value of minus the infimum of x. If that is not an upper bound for this set minus x here, then that would mean that there is a little element inside that set, which of course is of the form minus little x, because there's some element over in the original set x that multiplied by minus 1 has to give that element, because that's the definition of this set. So there is some element minus little x that is strictly bigger than it. So that's what we've got here. Now, of course, what we can do is just multiply both sides through by minus 1, which will flip the sign of the inequality. So we'll then have x is less than the infimum of x. So its corresponding element back in the original set, the element little x, so little x is guaranteed to be in big X, is now of course going to be strictly less than the infimum of x, which is a contradiction because this is a lower bound for the set capital X and little x is in that set. So it has to be less than or equal to every element, and here we have that this is strictly less than this. So it contradicts that being the infimum. So you cannot have such an element in this set minus big X that is strictly bigger than minus the infimum of big X. So yes, this number is an upper bound for this set. Now let's prove that it is the least upper bound. So for that we need to again do a proof by contradiction. So let's suppose that it wasn't. That would mean that there is some element, which I've drawn here in blue, u, that is strictly less than it, so strictly less than minus the infimum of x, and all of the elements in the set minus x are less than or equal to it, so it is still an upper bound. So for all the elements in minus x are of course from the original set big X just multiplied by negative 1. So for all little x is an element of big X, it must be the case that minus little x is less than or equal to u. So if it's not the case that this is the least upper bound, for the sake of contradiction we're assuming that, then there would be this u, which is an upper bound for this set that is strictly less than this, and it being an upper bound for that set means that this is going to be true. Now, how does this result in a contradiction? Well, of course, it's going to have a corresponding value on the other side. So if you take minus u from this inequality, multiply both sides by minus, you'll get that minus u is strictly greater than the infimum of x, which is pictorially obvious again, so the additive inverse of it, the mirror image of it, if you like, is going to be strictly greater than the infimum of the set x here. And the problem is now that this value here is still, if this is going to be true, is still going to be a lower bound for the set x, contradicting the infimum of x being the greatest lower bound. So let's see how that holds true. Well, just modify this here. So if for all x in capital X this is true, then multiplying this by -1 is still going to be true. So you'll get that x is greater than or equal to minus u. So if this is true for all x, then this is true for all x. So we have that for all the elements of big X, they're all going to be greater than or equal to minus u. So minus u is therefore a lower bound for the set capital X, but it's a lower bound that is strictly greater than the greatest lower bound, which is a contradiction. It would contradict this being the greatest lower bound. So therefore there cannot have been this element u that was smaller than minus the infimum of x, but which was still an upper bound for the set minus x. Otherwise it would give rise to this element minus u, which is a lower bound for the entire set x, but is greater than the greatest lower bound for that set x. So what we have overall therefore proven is that 1 minus the infimum of x is an upper bound for this set minus x, and 2, it is the least upper bound for that set. So we have therefore proven that minus the infimum of x is going to be the supremum of negative x. So we've proven this top one here. Just to then talk you through the bottom one, it's pretty much the exact same argument. So we want to show that minus the supremum of x is going to be the infimum of negative x. So we need to show that this is a lower bound for negative x and that it is the greatest lower bound. So to show that it's a lower bound, again, proof by contradiction, if it's not a lower bound, that would mean that there would be an element that would be strictly less than it, an element over here on the picture, but then of course its mirror image element over here would have to be back in the set capital X because it was in the set minus x. There would have to be a corresponding element over here, its mirror image element, that would be in the set x. You'd have this mirror image element that of course is going to be strictly greater than the supremum of x, which is a contradiction because that has to be an upper bound. So that's how you would prove that it is a lower bound for this set minus x. To prove that it is the greatest lower bound, we would have to show that if there were an element that was greater than it, that would lead to a contradiction, that was still a lower bound, that it would lead to a contradiction. So again, we can imagine that there is an element that is strictly greater than it, that is also a lower bound for the set minus x, i.e. it's less than or equal to all the elements in this set, but of course its mirror image over here would be a point that's strictly less than the supremum of x, and because the one here was less than or equal to all the things in minus x, the mirror image point over here is going to be greater than or equal to all the things in the original set x, meaning that it's going to be an upper bound for the set x that is strictly less than the supremum of that set x, which is a contradiction. So that's how you can show that this value is indeed going to be the greatest lower bound, the infimum of minus x. So there are those two results proven.